right, we should be back.
Here, Bill.
Oh, now it is showing me 30 frames per second, 29, 28. Uh-oh. Jeff says we're back. Jeff, is it less lag? No lag? Awesome. Okay, so the
Oh,
resolution should
beautiful.
be a little bit lower, but well, as long as it's not lagging. Okay, and we're up to 7 viewers now. Wow.
Oh, yeah.
Down Bad Productions, thank you for following. Everyone, please make sure to follow Matias too. Matias, wait, should I advertise your? Can I
You
even
may.
type it?
There's nothing there yet, but M471415 V8, but it doesn't. Nothing there yet.
But you're gonna start streaming, right?
I will. I will.
All right, so let's get into it. We've spent half an hour doing some debugging, but Matias is gonna tell us about Pick's theorem. Matias, are you AI?
Yeah.
You have a no. Are you
Oh,
version 8?
yes. I'm version
Are
8.
you watching the chat
Uh,
so I don't have to
I
read it
am.
read it
I'm
out loud
keeping an
to you?
eye on it. Yeah. With a little bit of a delay, I think, but I'm watching it. So yeah. You want to hear about Pick's theorem? It's a really, in my opinion, it's really simply stated, very easy result, uh, and just absolutely beautiful in my opinion. So I'm delighted to share it. If you haven't heard of it before, I think you're in for a treat, and it's an easy one to share with your friends and uh, non-mathematicians. And it's also relatively famous, but not. It's in the top 100 for sure, but not like in the top 10. Uh,
I
I
got
mean,
through
it's
grad
in my
school without
personal
learning
top
about
10.
it.
Yeah, so so it's a little bit niche, but it's really neat and very simple. So I think you'll enjoy it. So what's the theorem? Well, the theorem says that let me write it here. For any uh, lattice polygon, or also known as integer or integral polygon. And let me add the word simple there. Simple integral polygon. This wild claim is true. We have that its area is equal to the number of interior points plus the number of boundary points over 2 minus 1. And we're going to do an example in a little bit, but just to spell this out, what everything is. So the A is for area. Um, I is, and I use this notation as a combinatorialist, the number of, hashtag for the number of interior points, and I should say interior lattice points. That'll be clear. And then B is the number of boundary points. Write a little slower, more clearly. So, for example, if you look at this polygon P in the blue on the left,
Mm-hmm.
then we can obviously figure it out its area with some basic geometry. But this is the fun way that we're going to do it. And it's so the area, let's verify that theorem holds in this case. Its number of interior points in this case is how many? How many would you say are interior in this?
I only see one interior point.
Exactly, yes. And how many boundary points do you count?
Oh boy, let's see. One, two, three, four, five, six, seven, eight, nine. I see nine.
Good. All right, so the claim is that the area is then 1 minus 9 over 2 minus 1, which adds up to, oh, the ones can't, oh, sorry, there's a 9 wrong there. 1 plus 9 over 2 minus 1. So the area is 9 over 2 or 4.5. And you can verify this by counting some triangles in the
That's
picture.
what I'm working on. Yeah. Ugh,
Very good.
arithmetic. Hey, I got the same answer. So I did
Great.
this top triangle and then the trapezoid and
Yep.
then that bottom
Mhm.
triangle there.
Nice. So this, we're going to prove this, but it works in general for any simple integral polygon. So maybe I should say what that is,
That was gonna be my
so that
next
you know the
question.
rules. Mm-hmm.
I know what
So
polygon means, I
simple
think.
polygon, yes. Uh, I don't have a good definition of a polygon. I mean, it has sides and vertices. I didn't
You know it when you see it.
uh, exactly. It's one of those things. Uh, but simple means that it doesn't have any holes. So uh, it's you can't have like a torus or a two-dimensional torus. And integral means that the vertices uh, are all
Lattice
on
points.
lattice points.
Yeah.
Yes.
Okay.
So a fun consequence that I mean it's non-trivial, but one fun fact that follows from this, at least I think it's fun, is the following: that well, every triangle that has no interior points, it has integer coordinates as the vertices,
Uh huh.
as area 1/2. And it's obvious for like simple triangles, but you can have some really thin triangles put into your uh, integer lattice, and as long as there are no interior points, you
Oh.
just have the area will always be 1/2.
Huh.
Yeah. So, and you can, of course, do very complex integral polygons, and the area will always be counted by this formula, as we shall see. But one reason I like this theorem too is the proof. Well, there are lots of proofs for it. Some are very, some are more clever than others. We're not going to go through some of the most clever ones, but some of them use some higher machinery. And for example, Minkowski's theorems for bounding polygon area or convex polygons and things. And we're going to use an inductive type of proof, but I like this because it's an unusual inductive proof in a neat way
Okay, sorry, I
because you
messed
kind
up
of
the board again somehow. I don't know how this happened, but um,
can you just control Z?
I don't know. Um,
Send it to spherical polygons, please. Hmm.
how far was I zoomed in before? Darn it. Um,
Zoom out a
uh,
little bit and
wait. Okay, I think I fixed it. Yes. Okay. And yeah,
right.
I should have mentioned. Don't write too close to the side to the that
Yeah,
rectangle.
I
It's
see it.
not perfect. But okay, I've restored it. I don't know how I did that. Sorry. We are new to this streaming setup. Um, and I I'm neglecting my duty as the host here. I should have given a shout out to Eda the Two Eye Pie, who has been in the chat. Who's another math streamer. Um, Sorry, Zach, I missed most of your stream today. Right after I sent you those messages talking about the stream we were gonna do today, one of my other friends called me and I had to leave, so I missed like all of it. But thanks for being here. Okay, so you're gonna tell me about a cool inductive proof of this?
I think it's cool. I mean, it's a pretty standard inductive kind of argument in uh, geometric combinatorics and geometry. But the cool thing about it is just typically, at least I didn't see anything like this in undergrad because uh, most inductive proofs I encountered were in more in like elementary number theory and things like that, where
Mm.
it's you're always inducting on the integers and on your base case, and then everything just flows from that. And this is kind of simple, but because it's geometry, you kind of uh, well, I won't spoil it. We'll work it out. But we're going to do some base cases first. So here is a triangle T. So this is a rectangular triangle. Do you know what a rectangular triangle is?
I
Any
would,
guesses?
well, based on the word rect angle meaning right angle.
Ah,
Well, oh,
that's
okay,
a
well, we have a
good
name for
guess.
that. That's a right triangle. So does this mean something different?
Yeah, exactly. I am having trouble writing and uh, at the same time as speaking, but it means that the at least two edges, exactly two
Oh,
edges, I should say,
oh,
are
two
parallel
edge.
with
Yeah, okay.
coordinate, mhm, parallel with the
So
axes.
in particular, it's a right triangle, but it's also oriented
Yes.
nicely.
Hmm.
Okay.
Hmm. So two edges parallel with axes. If we have something like this, then we're going to prove it for this base case. So how would you count the boundary points of something like this?
Yeah, the boundary points. So I'm going to see a plus 1 boundary points along the bottom
Yep,
and b plus 1 boundary points on the right side. Now I've
similarly,
overcounted
yeah.
by
Hmm.
1 because I counted the bottom right point twice. So I think it's just going to be a
Yes,
plus
yes.
b plus 1. And now I want to think about the. Ooh, this is a little weird, I feel like. I want to think about
Hmm.
the hypotenuse. The hypotenuse the hypotenuse might have some boundary points. Like if it's
Yes.
a 2 by 4 triangle, you're gonna have one boundary point. Okay, I have a thought, Matias,
Hmm.
which is I'm inclined I want to think about making another copy of this rectangular triangle and filling in the rectangle.
That's a great thought. You want to do that now for
Oh, wait, I can draw on
counting
the board.
the. You
I can
can.
draw when I'm
Uh,
there. That's the triangle that I want to
mhm.
draw in because that'll make it way easier to count all the points.
Will it help you with the hypotenuse?
Oh. Hmm. Yeah, it's not immediately obvious to me how.
Hmm.
Oh, darn.
Okay. Well, I'm gonna write it as whatever d for hypotenuse, and so the number of points on the hypotenuse plus one, but we've overcounted again. And then we're gonna subtract 3 from this as we've
For
overcounted
the
at
three
each.
vertices, yeah, which have all been
Yeah.
counted twice. Okay.
Yeah. Uh, so the question is, what is d?
Yeah.
So it is um, the greatest common divisor
I
of
was
a and
I,
b.
I swear I was about to say that.
Yep. Yep. Hmm. So you can think of greatest common divisor of A and B. It divides A. So then there's this piece left over. Perhaps we should do an example to make it more clear. So I guess this has, based on the picture, is equal to 6 right here, and B is equal to 3. So this side length 6 and 3,
Yeah,
and
so it would have ones at like 0, 0, 1, 2, sorry, 2, 1, 4,
mhm,
2, and 6, 3.
mhm. And so you can think of, after dividing A by the greatest common divisor, you get 2, and after dividing 3 by the greatest common divisor, you get 1. And that gives you like this unit, little, or not unit, but this small piece of the triangle here, first lattice point, and then the number of times it appears is it's scaled
Yeah,
by the
scaling
greatest
like
common
the
divisor.
hypotenuse vector,
Mhm.
and I want to scale it down so that I still get integer components. That means I need to, yeah, divide by something that divides both A and B.
Mhm. Exactly. And so then this formula for B, the boundary points, is just A plus B plus D, where B is, oops, B is the greatest common divisor.
Oh, that's gonna get cut off, isn't
And
it?
I'm going too close. Yep. I'm just gonna say this. Okay. Now let's move on to interior points. Now we can use your intuition that was relatively immediate for counting points. We're gonna double the triangle into a rectangle, just like you said. So use a
Okay.
But we're gonna,
So,
yeah, if you have ideas, go ahead.
yes, the number of interior points for the rectangle should be a minus 1 times b minus 1.
Yes.
Uh, and then
And you're talking about the interior rectangle. You're really
oh,
talking about
oh,
this.
yeah, yeah, yeah. So points
Hmm.
that are inside the rectangle. And now I need to subtract out the number of points in the hypotenuse and then divide by 2.
Exactly.
That'll give me all the ones that are interior to the original triangle.
Exactly. Yes. And wait, would double make it easier to count boundary points too? Doesn't apply to rectangles. I'm not exactly sure what you mean there, Jeff.
Because,
But I,
yeah,
but I
that's what
think
I
you said
wanted to
never
do
mind.
at first, but it doesn't, yeah, it doesn't help you out with the hypotenuse.
Right. Exactly. It doesn't help with the hypotenuse. So wouldn't boundary points include multiples of the greatest common divisor?
I think that's what we
Yes.
were saying, essentially.
Right. So the greatest common divisor is not the scaled little vector there. The greatest common divisor tells you how many times that vector, how many copies of it gives you the whole hypotenuse. And so that's why it's the number of lattice points on there, plus then one at the end, or the one starting at the origin. So great question. Yep. But Justin, as you were saying, if we have this interior square, or sorry, rectangle, the number of lattice points in there, or integer points, would be just like you said, it would be a minus 1 times b minus 1. And then what we're going to do is subtract the number of lattice points on the hypotenuse, the interior hypotenuse of the interior rectangle, which is would then be d minus 1.
Yep, so now you've got the
And
ones
so
that
that
are interior to one triangle or the other,
correct.
but not on that
And so
boundary.
then by symmetry, we just divide by 2
Yeah.
to get the stuff that's inside the
And I'd be willing to bet,
triangle.
Matias, that now if I took a plus
Mhm.
b plus d
Mhm.
and divided that by 2, and then added
Mhm.
that to this fraction we just wrote down, and then subtracted 1, I
Mhm.
bet we would get 1/2 AB.
I couldn't quite follow, but
I'm saying
I'm sure
compute
you're right.
compute the I plus b over 2 minus 1 and substitute in the values
Yes.
we just computed.
Yeah.
And I think we're going to get
Right.
1/2 AB.
Exactly. So we can expand AB here, minus A minus B plus 1 minus B minus plus 1, all divided by 2. Oh no. Sorry. Thought I messed them up, but I just moved the screen across.
you can you can move the screen on.
Yes, and I thought I screwed it up for you, but I realized it was just for me. So I moved myself back and all is good.
Yep, yep. You can move the screen around all
Now,
you want. Um, if I move it around on my browser here, then we have
yes.
problems. Hey,
All right, so
Femvox
if you,
fan, welcome. Haven't seen you in a while. I mean, I haven't been streaming in a while. But yeah, my grad school buddy Matias was telling me about Pick's theorem. I'm sure you told me about this at some point in the 5 years that we had desks next to each other, but I had totally forgotten about it.
I don't know that I did. Maybe I did.
I, I,
I'm sure I did.
I feel like I heard about this from someone at some point.
Yeah. Mhm. But if you do the algebra here, then what you just get is AB over 2, as expected.
Oh wow, like everything just cancels out except that
Yep.
AB at the
Yep.
beginning.
Yep. So minus A over 2 cancels with that A over 2, minus B over 2 with B over 2.
Okay. So
Yeah.
okay, maybe not super
So,
impressive to do this for a rectangular triangle, but the cool thing is going to be how
mhm.
this all combines together.
Yeah.
Like I'm already thinking about how when you merge two triangles, the boundary points on the edge that you glue them together,
Mhm.
those are going to become interior points.
Yes. Yes.
And so they're going to contribute to I now, whereas previously each of them was contributing to the B over 2. So those one halves together. Okay. I don't see the whole thing, but I think that's one of the big ideas.
Yeah.
All right.
Yes.
Take me to the
Very
next
good.
step.
All right. So the next step, we can kind of go quickly, but this is actually just for uh, rectangles that have two parallel edges with axes, or I should say all four of them are parallel with axes. So I don't know if we should call those rectangular rectangles in line with the name of rectangular triangles. But that sounds
Grid-aligned
pretty,
rectangles.
yeah, something like that.
GARs. GARs.
Mhm. So this is actually much easier than the case that we just did
Well, then
with
why
the
didn't you let me
triangles.
start with that one, Matias?
Uh, it's fun to start with the triangles. I don't know. Triangles are more basic in a way, in my mind. So,
You would think
but this
that.
is exactly the same
Yeah.
thing, and this is easier. So now, if this is A on this side, this is B, then we have,
So
like you
I is
said,
going
the
to be the
interior
A
points.
minus 1, B minus 1 again.
Yep.
And then B is going to be. I just noticed that we're using B for two, well, lowercase and capital B. Um,
There
but they're different. They're different. I just didn't even
they
notice.
are.
Um, so that boundary points is going to be a plus 1 plus a plus 1 plus b plus 1 plus b plus 1 minus 4. So 2a plus 2b? Oh, yeah, like of course, it's
Yes.
the perimeter.
Yes. Exactly. And then divide by 2, minus 1. And again, like
Can I
before,
ask,
everything cancels out, but maybe. Hmm?
is the number of. Oh, no, 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 no. I was going to ask, is the number of boundary points always the same as the perimeter? Because it was for our first two examples, but that's definitely not true in general.
No, no. This is, I think, just a property of the fact that we're grid aligned.
Oh, wait, that's not even true in the first example. I was looking at a plus b plus d, but d isn't the length of the hypotenuse. All right, just ignore me. Okay,
So,
we got ab.
so as a combinatorialist, we sometimes stretch the definition of length, especially in these lattice point type of problems. And so, normalized length, then everything works out. You just normalize everything, and then it's fine. But anyway, so those are our two base cases. And what are we going to do with from here? We're going to do exactly what you suggested, or we're inclined to think. But let's see which space we have. Go over here. General case. It's going to look something like this. We're going to have some sort of polygon P. Then we're going to split it half into two pieces, P1 and P2. And so now we have EI is the number of boundary points of PI. II is no, not boundary. Interior points.
I messed the screen up again somehow. I don't know how I'm doing this because I'm not touching my computer, but somehow doing something on my iPad is moving. This is weird. I don't know why it's doing this.
I have to erase something soon anyway. So looks like you're still setting it up.
Yeah, sorry. Okay. It's good.
Nice.
Famished
So
Integral,
now,
hello and welcome. Okay, so yeah, interior points of PI. Oh, yeah. Yep.
that's just notation. So we have this polygon P, split it up into two smaller ones, and you can kind of see the inductive nature that we're going to go for here. If Pick's theorem holds for P1 and P2, it should hold for P, right? Because, well, area is additive.
Yep, I
If I
believe that.
add two areas of, right? So it should also hold for the Pick's identity. So we should do this, but now we need a little bit of extra tool here, or just notation wise, call this line L. That is the one that divides this polygon into two. And now with L, how do we describe or relate the interior points? Let's start with those. I for the whole polygon to the pieces P1 and P2. Well, we have the interior points of P1. A little different color here. We have these guys here. We have the interior points of P2. We add them up. Stuff along this line L that are also interior. But if we add the whole line L is the number of points, I guess, on this line, to abuse notation a little bit here, and then subtract the endpoints.
Right.
So that's how we relate the interior points of the whole to the interior points of the pieces. So how about boundary?
That should be
Yeah,
B. Yeah, B1 plus
Hmm.
b2, but now you've
Hmm.
double counted. I'm getting confused about the the endpoints again, but you basically double counted L. So you want to subtract out an L.
Actually, want to subtract both L's out, right?
Oh,
Because you've
of course, because those are no
added it
longer
twice. Yes.
boundary points, except
Yes.
now you got to add 2 back in, don't you? So that you actually do have.
Yes. Yeah. Exactly. Okay. I'm out of space now, but I think I can remove the base cases from the right
You got
there.
like one more good line right there.
Yeah, but it's going to be a long one, so I want to cram
Oh.
it. Let me. And delete. Boom. So now that we've related the interior points and the boundary points from the with big polygon to the little ones, now let's see what happens with the identity. I plus b over 2 minus 1. You just substitute the stuff in. I1 plus I2 plus L minus 2. And then plus B1 plus B2 minus 2L plus 2, all divided by 2, minus 1. Then you rearrange, and you get what you would hope for, which is I1 plus B1 over 2 minus 1 plus I2 plus B2 over 2 minus 1. And of course, this would be the area of P1. It's supposed to be. We have this. This doesn't prove anything really yet, except for this kind of additive property of that holds in general for a polygon. So that if you, because we know area is additive.
Yeah.
Uh,
It feels like we're basically so what to me feels
yeah.
like the only thing that's missing is an argument that any simple integral polygon can be
Hmm.
decomposed into a almost disjoint union of grid aligned rectangles and rectangular triangles.
Yeah.
Because we just
That's.
did an inductive step
Hmm.
basically. We did our 2 base cases.
Yeah.
Subtractive.
So it's additive, which is also subtractive in the following sense, because now uh, what this is saying is that if Pick's theorem holds for P1 and P2, then it holds for P, right? But
Yeah.
it's because of the algebra we just rearrange. It also says that if this is true for P and P1, then it's true for P2. Like you can
Oh.
cut out a
Yeah.
piece if you know that it's true for the whole and also for a part, then it's going to be true for the other part as well.
So
So that's
instead
what I
of
mean by subtractive
yeah,
here.
so instead of breaking down my polygon into the 2 base cases, I could just add on those 2 kinds of nice shapes until I have a rectangle. Like I'll
Mm-hmm.
illustrate what I'm saying. in the example, if I add on all these little triangles and I guess one square, eventually I get to a rectangle.
Hmm.
So is this really two totally valid ways to proceed with the proof?
What was the two valid ways?
Yeah, so like I could break the shape down,
Yes.
or I could add on things
Yes.
until I have a rectangle.
Hmm. Yeah, so that's what we've shown here essentially. I mean, you just rearrange the algebra a little bit to
Yeah.
show that P minus P1 is same as P2 essentially, where the identity holds. So we've shown in this step kind of two directions. We can either add or we can subtract. And when we're subtracting, we have to know it for the whole and then for the part that we're subtracting.
Mm-hmm.
This is kind of where it's like an inductive argument, but it's kind of unusually, or they just work a little bit different in geometry sometimes because you end up having to deal with odd cases. And what we really want as our base case is an arbitrary triangle, because an arbitrary triangle or any arbitrary polygon can be triangulated into triangles. And then if we know it's always true for arbitrary triangles, then we can build the polygon up from those arbitrary triangles and it holds for the whole polygon. So we've done these two weird base cases,
Oh,
but they don't prove it directly, at least I haven't told you how, for an arbitrary triangle. But we'll use them to help us.
is the so to me,
Mhm.
like I'm convinced at this point, but
Mhm.
I'm
Mhm.
sort of using my intuition to say that I can break down all the shapes, any such polygon into our two base cases, or I can tack on stuff to get a rectangle. But that's not,
Mhm.
that's not very rigorous. Are you saying that we want to like there is a rigorous proof that any
Uh,
polygon can be
so that
decomposed into triangles, and we want to use that?
I was going to claim it as a fact. There's a simple procedure you do to triangulate a lattice polygon. I mean, I think you would be convinced that that's possible
Yeah, yeah, yeah.
always.
But I guess my point is just
Mhm.
I'm already convinced of the theorem. Like, why?
Ah, okay.
What? Yeah,
Ah,
what's
okay.
missing?
All right. A picture is missing. Proof by picture. So what we're really missing is how do we know that this holds for an arbitrary triangle? There's just a little bit of an argument there to because we've only showed it for rectangular triangles and also for rectangular rectangles, but you'll be convinced after I draw a picture that it's true for the case of arbitrary triangles as well.
Oh, this is where the subtractive approach is much easier,
Yes,
right?
exactly.
Yeah. Okay.
Hmm. Also P1 and P2.
I guess yeah. I just kind of already believe that what you're about to do with this arbitrary triangle, I believe that you can do that with
Hmm.
any
Hmm.
simple integral polygon, but I do see this is nice. Um, it's a tighter argument if you do this for
Yeah,
triangles and then appeal to the fact that any polygon can be decomposed or can be triangulated.
yeah. So if I just let me draw a little bit of a better polygon here. So if something like this, you just you pick a vertex and you can just start drawing triangle, like triangulate it. And sometimes if it's not convex enough for you, then you can just start at a different vertex, and you can always break it down into triangles. But one easy way is just starting at a vertex and then making the smallest triangle possible, or connecting it to the vertices going around clockwise, for
Yeah,
example,
so Femvox fan in
as
the
you can.
chat is suggesting what we're gonna do with the general triangle, which is to yeah do a rectangle minus three rectangular triangles.
Exactly.
Uh,
Great. Great. So a general triangle, it could look, I guess there's really two kind of cases that you would consider.
yeah, a containing rectangle. It's like the smallest
Exactly.
grid-aligned rectangle that contains it.
Yes.
The grid-aligned rectangular closure.
Hmm.
The
Very good.
the con the rectangular hull.
Circumscribing
This,
rectangle.
sir, did you say
I think it's describing
circumscribing?
rectangle.
At most, do you maybe also need to put in a rectangle sometimes? Like, let me draw what I'm
Yes,
thinking.
and here's why. Yes, good.
I'm thinking about something like
That's
this.
why. Exactly. Yes. So if now we draw the box around here or the rectangle, now you also need this rectangle. Boom. So once you subtract all of the triangles and now this rectangle, what you're left over with is a general, that type of general triangle.
Are these like the only two
Yes,
types? Okay. I don't even know what
essentially, yeah.
type means precisely.
Mhm.
Is it wait,
These are the two types.
is it just whether it's acute or obtuse?
Yeah.
Huh.
Uh, but so you can have a. It's not necessarily true that if you have an obtuse one, then you need a rectangle. But of
Oh no, you're
course,
right. Yeah, like
yeah,
that
you
one.
could
Yeah,
have.
yeah, exactly. And there you only even
Yeah.
need two triangles. Huh. I mean, but you could like if you wanted to make this precise, you could just do some kind of annoying casework, I
Yes.
assume. Do as a a polytope theorist, do you do that kind of annoying casework for something like this, or do you just say, "Come on, I
uh,
mean, like, look at it."
I I depends on how convinced I am in my own mind, I suppose. Uh, and it varies by day. Sometimes I'm like, it's this is obvious, and but it, I don't know, with these geometric things, especially in higher dimensions, man, it gets really like intuition goes out the window so fast that
Oh yeah.
I have to go casework. So you've heard of Erhard theory, just being in uh, circles that
Oh, I've heard of
run
it.
together,
Yeah.
run together. Yes. So that's this in three dimensions, or in arbitrary dimensions, I should say.
Oh, okay. I was about to ask how this generalizes, but okay, that's what
Mhm.
Erhard theory is. Okay.
So there's not a no longer than a nice identity like this, but there's still things that hold, and you get to
Oh,
use
yeah.
polynomials and versions of polynomials to things. How many lattice points are inside a general polytope? Yeah, that basically concludes the proof, and we'll draw a rectangular rectangle and to indicate the completion of the proof.
Nice, and you almost fit it into one slide. Almost.
Almost, yeah. But isn't this crazy? Like you can draw any sort of shape as long as the vertices are on integer points, and then You just count interior points and boundary points, and that gives you the area without having to go through the tedious work of doing all the triangles.
That's pretty nice.
And one thing that didn't come up, but I know you know about, is the shoelace formula, which uh, you told me once about. But
What?
that you can also. Oh, okay, you don't remember?
I don't
Oh,
remember.
so there's another nice way to count the area of a polygon like this using what's called the shoelace formula, and it's there you actually have to know the coordinates of the vertices specifically. So this, what we talked about today, is doesn't depend on the actual coordinates. You just need to know the
Yeah.
interior and boundary points. But if you know the coordinates of the vertices, there's another formula that you can use to just uh, take a bunch of determinants of 2 by 2 matrices and add them all up and then divide by 2 to get the area.
This
So
doesn't feel like a thing that
that
I ever knew.
really, I I feel like you told me about the shoelace formula because you were like, oh, this is a cool thing that you can do with determinants or something.
If I did, it's completely gone from my memory. Wow.
Or maybe I just made it up,
You
but
you might have.
I feel like I learned it
I'll
from
take
you.
credit for it.
Sure, sure,
What you might be
by all
thinking
means.
of is that you taught me how to tie my shoelaces, literally.
That's true.
And to be clear, if anyone's watching,
Without
I
using the
knew how to.
formula.
To be clear, I did know how to tie my shoes before, but Matias taught me a fun alternative way, which is still how I tie them, all the time. Yeah.
So this is Georg Pick's famous theorem from 1899.
Wow, that's pretty cool.
All I got for you today.
All right,
And I think you now owe me some of your math.
I do. I have some cool math of a totally different flavor. So, any last words before I erase everything?
Of course, if there's questions in the chat, you're welcome to as well. Ask.
But only if you ask before I make it all the way around with the eraser and lasso. I'm not sure if I got that period. I might have to come back for it. I've got it all selected. Here we go. Oh, shoot. Undo. I killed the box, too. How did that... Okay. Oh, I just duplicated it? Oh my goodness. Help me out, Matias.
I'm lassoing some stuff out of here too.
Oh, that's funny. I can see your cursor move, but I don't see the lasso.
Yeah.
I assume you're seeing the same thing.
Hmm.
Okay. Go team. We erased it all. Alright, let me pull up my notes. Okay, I did tell you roughly what I was going to tell you about, right? Do you
Yeah,
remember?
but I forgot.
Okay.
No.
So, what I want to tell you about is, I guess where this came about was, I think this was actually while I was coming up with some ideas for streams that I did for Calc 2 this last semester. But I got thinking about like all of the different ways to characterize the exponential function. and how you can, or even just the number e, um,
Mhm.
and how you can relate them all. Like you, of course, you can define e as a limit in a couple of different ways, and
I
uh,
only know of one.
oh well,
Oh,
there's
I suppose the like power series expansion. Are you counting that as a?
what am I thinking of? So there's definitely the limit as n goes to infinity of 1 plus 1 over n to the n.
That's the one I'm thinking of.
Yeah.
The only one I know.
Maybe I am thinking about like the sum from n equals 0. Why is it sum from n equals 0 to infinity of 1 over n factorial? Sorry, I'm struggling to write here.
Mhm.
I feel I I feel like there's something else that I'm just totally blanking on. But that would come up like in a Calc 1 class. No, no, no. I think. Oh, you know what I'm thinking of? Is that the limit as h goes to 0 of e to the h minus 1 over h is 1. So this is the the limit that
Mm.
shows up when you try to compute the derivative of e to the
Yes. Yeah.
x.
Yeah.
Um, and
Hmm.
so, yeah, these two things are the things I'm thinking of. They both show up in Calc 1. These both sort of uniquely characterize you know, the number e. So I was thinking about that, and then there's also the power series.
Hmm.
Um, and then, you know, one of the ideas that came up as I was looking into this is that actually maybe comparing all the different ways to describe e isn't even the best thing you could do. You might have a better time if you do a seemingly more complicated thing of looking at the function e to the x. Um, and there you get some other characterizations, like, first of all, e to the x is the unique function which is its own derivative and sends 0 to 1.
Hmm.
And then or e to the x is also the inverse function of ln of x. Now, normally you think of ln of x as the inverse function of e to the x, so how does this give you a new way to define e to the x? Well, you can oh my goodness, were you having any difficulty writing like this? Like it just stops writing for me all of a sudden.
Oh no,
Oh, okay.
it worked okay
That's
for
a
me.
personal problem then. But yeah, you can
Yep.
define ln of x as this integral. So take this function and invert it. That's another way to get the exponential function. So I was looking at all these different ways
Mhm.
to define the exponential function and how you relate them. Like I was trying to prove, like, you know, to get between all the different definitions. Um, but then I really focused. I got focusing on this one, and I learned that you can prove one of one of the properties of the exponential function, which is that e to the x plus y equals e to the x e to the y. I learned that you can prove this sort of directly from this definition, and that's where this topic that I'm going to tell you about got started. That's
Hmm.
where my investigation got started, and I found that you can actually you can prove pretty much anything you know about the exponential function directly from this definition. And at first glance, this doesn't seem that interesting. Like, of course, this implies everything else because that uniquely characterizes the exponential function. But the interesting thing is you don't
Hmm?
have to go from here to like any of the other definitions. You can just directly work with this one. So you'll understand that this also appeals to me as a category theorist. I think it's really cool that like you can prove everything you want to know about the exponential function just based on this description of what it does, a property
Hmm.
that it has, like a defining property, rather than sort of like saying what it is. Like I would say that if you want to say what e to the x is, like I would define it with a power series probably. Here's a description of what it is. This is just like a nice property that it has. Anyway, so I'm gonna show you how anything that you know about the exponential function, um, we can work it out in a really slick way from this definition, and then we're gonna do the same thing for the trig functions, for sine and cosine.
Nice.
Okay,
Nice.
so maybe yeah, what I'll do is I'll ask you, what are some things that you know about the exponential function? So let's just call this function e of x. I'm not going to write e to the x so that we don't start
Hmm.
thinking of it as the familiar exponential function and manipulating it in ways that that we're accustomed to. But we're just going to say that this is a differentiable function
Hmm.
um, from the real numbers to the real numbers. Oh my goodness, this is getting really annoying. Okay, we're gonna have to look at alternatives to Miro for next time.
Yeah.
Whoops, it's f now apparently. Now, e prime of x equals e of x, and e of 0 is 1. Whew, okay, maybe if I zoom differently. I mean, it's something weird about my iPad, or the app on my iPad. Okay, this is our starting point. This is all we're going to assume.
Okay.
Um, hey, Mean Machine Rex. Welcome in. We're talking about, we're doing some calculus. Um,
And about Elon Musk for person.
which which one of
Uh,
us looks like Elon?
I suspect that's me.
Um,
Elon
um,
doesn't wear glasses
okay,
as far
so,
as I know.
all right, so Matias, tell me, now that I've written this out, tell me things that you
Uh-huh.
know about the exponential function.
It's positive.
Oh, okay. And I'm gonna look up. I've got them arranged in a certain order, so I'm just gonna.
Okay, okay.
Uh, so e to the yeah, e of x is positive. Anything related that you want to add on here?
Increasing.
Yeah, I guess we could also say concave up, but
Sure.
that's and the third derivative is positive, and the fourth. Okay, the function is equal to its own derivative. If e is positive, they're all positive. Yeah. Yeah, Matias is also the mod Mean Machine Rex. Um,
Am I?
yeah, you're a mod. I also
Oh,
made.
okay.
I don't know if Zach is still here. I made him a mod too. I don't see him in the list of chatters, but um, Shazad is also a mod, but he couldn't make it tonight. Okay, so what else do you know about this function?
Other than that, its derivative is equal to itself. Um,
I've actually got 7 things.
wow, really?
Yeah.
I was going to use positive and increasing as two different ones. I'm already
No,
struggling
that's
for
one.
what. Then you're not looking for the other definitions,
No,
or
I'm not. Yeah, we're not trying to say what it is. We're just trying to say some properties. So here, I'll give you one to get you inspired.
all right, all right.
So for any integer n, e of n is the nth power of e of 1.
Uh,
Number 4 is really a step to number 5. Do you want to generalize that for me?
uh, well, my mind kind of went to the power rule, or that if you like, like the summing powers for exponentials. So I guess you have that
Are you saying,
up there.
is this what
Yeah,
you're talking about?
is equal. Yep.
Yeah. Okay. Where I was going with this is if you have a rational number, this
Hmm.
function is going to send it to e of 1 to the p over q, which of course means the same thing as the qth root of e of 1 to the
Hmm.
p.
Yeah.
Oh, Femvox fan is suggesting transcendental. Like like that the quantity e of 1 is transcendental. That's not one of the properties that I had in mind here. I think that one's I think that's hard to prove. Uh, I don't think that's an easy proof. Everything that we're gonna do here is pretty straightforward. You got any more ideas?
Hmm. Mm. Okay.
Okay,
Yep.
so that
Yep.
I think that follows from 2, but I think that follows from 2. But I'm gonna go the other way. I'm gonna prove 2 using 1. Um, Number 6 is that there's an approximation. I'm not doing the full power series, but I will say that e of x is greater than or equal to
Okay. Okay.
1 plus x. And the only reason that I want to do that is is to analyze the end behavior. The limit as x goes to infinity of e of x is infinity, and the limit as x goes to negative infinity is 0. Oh, so you're just watching the screen on. Oh, no, sorry. You're watching the whiteboard. You're not watching the stream.
Correct. Correct.
Whew. Okay. Um. All right. This looked like a good list of properties.
I think it's pretty great.
All right. So first, I'm going to prove that e of minus x is 1 over e of x. And I'm going to do this by looking at a function. Oh. Which is e of x times e to the minus x. No, your knowledge of the exponential function should suggest what f of x is, or what it will simplify
0.
to, right?
Mm-hmm.
But
Or e to 0, which is
yeah. So how do I show that? I'm going to look at the derivative. Okay. I'm going to try flipping my iPad upside down. Probably won't fix this, but um, so the derivative using the product rule is I'm differentiating the e of x first, and then I'm leaving the, oh, it did not fix it. Leaving the e to the minus x alone, sorry, e of minus x. And then I'm going to leave the e of x alone and differentiate the e of minus x, which by the chain rule is minus e of minus x. Okay, so that's 0.
yeah.
So f is constant. So for all real numbers x, f of x is equal to f of 0. Doesn't matter what value I plug into this function, I always get the same thing. And it's shifted again in the stream. All right, fixed. So f of x was e to the minus x, or e of minus x times e of x. And this is supposed to be equal to e of 0 times e of minus 0. Which, of course, is 1 times 1. I wonder if I'm, like, touching the zoom thing. Huh, okay. So, yeah, now divide over e of minus x is 1 over e of x. There we go. First property.
Very good.
All right, number 2. We're trying to show that e of x plus y is e of x times e of y. So the strategy for all of these properties, well, not all of them, but but we're going to use this idea a lot. We're going to show that a function is constant by showing that its derivative is 0. So I'm going to fix a particular real number y, and then we're going to look at the function, maybe we'll call it g of x now. We're going to let g of x be e to the x plus y times e to the minus x. And, if this is true, this function should be equal to e to the y, or e of y, which is a constant. So if I differentiate, I should get 0. Okay, I'm differentiating the first term, and now I'm differentiating the second term. Hey, we get 0. So g of x for any x is the same as g of 0. G of 0 is e of x, e of 0 plus y times e of minus 0. That's just e of y. And then to finish this off, we use property number 1. So I've proven that this equals this. Now multiply both sides by e of x. And over here, that'll cancel out the e of minus x.
Right.
All right. You with me so far?
Yeah. So is the strategy going to be always pick a clever function like g of x here and take the derivative?
For a lot of these,
Hmm.
though actually maybe it was only 1 and 2.
Mhm.
I
Okay.
think everything else is basically going to follow from this.
Mm.
So for number 3, um, how do I know it's positive? 3 actually follows from 1 immediately. If I proved that e to the x times e to the minus
Right.
x is always 1, e to the x can never be 0 because there's nothing you can multiply it by to get 1.
Right. Yep.
So that proves that it's never 0. How does that tell you that it's always positive? This would be a great question to ask my Calc 1 students. How do you know it's always positive, given that it's never 0?
Well, I don't know that it's continuous yet, right?
Well,
So
we
given that it has
do.
a positive value, okay, so I know that E0 is 1.
I'm assuming it's differentiable,
Sure, okay,
which of
right.
course you
Hmm.
have to assume for this to make sense.
Yes, yes, right.
Yeah.
Yeah, yeah, yeah.
So yeah,
That,
that means it's
of course.
continuous. That means the intermediate
Mhm.
value theorem applies, and so if it's positive
Yes. Okay.
somewhere, it's positive everywhere. Because if it weren't, then it would have to cross 0. Okay, so now we know it's positive, and because it is equal to its own derivative, that means its derivative is always positive, which means that e of x is always increasing, and so on. We already kind of talked about that. Once you know that e of x is positive, all of its derivatives are positive. All right, so that's 3. Number 4. Number 4 uh, is just induction with number 2, right? So when n is 0,
Hmm.
e of
Yeah,
0 is, well, we already know that that's 1, which is definitely
right.
e of 1 to the 0. When n equals 1, e of 1 is, well, that's 1 plus 0. Wait, sorry. It's it's not that complicated. E of 1 is in fact e of 1 to the 1. It gets more interesting now when you go on to bigger integers. But property number 2, immediately tells you
Mm. Yeah.
what you want. And it continues like this. And the negative integers follow from the positive ones. And property 1. For number 5, you could fill in the details, Matias, but I think this is nice to show. We know from number 4 that e of q. Is that what I wanted to do? No, e of p is e of 1 to the p.
I think you shifted the whiteboard again.
Ah, I'm gonna find something other than Miro to use next time. This is super annoying. I don't know why it keeps moving. Or I could learn how to use frames here.
Hmm.
It's also not, it doesn't jump, it doesn't adjust consistently. Like I hit the arrow keys and sometimes it moves a little bit, sometimes it moves a lot. I don't know if you're seeing that on the stream. Thanks to all of our viewers for putting up with all these technical difficulties. All right. So,
And for putting up with you.
no, arguably the more obnoxious thing.
Hmm.
We've got 8 people viewing right now. That's crazy. Do you have like 7 other windows of this open, or?
Yeah.
Um, okay, so I guess then what?
I
Why
think
is
you did it again. Looks like. Oh, you're
what?
safe, I think.
Okay, so e to the p is the same thing as e to the p over q times q.
I agree.
And similar to what we did in number 4, well, because q is an integer, you're going to be able to break this up as e to the e of p over q to the q.
Mhm.
Yeah, that's just repeated applications of property number 2. But now if e of 1 to
Yep.
the p equals e of p to the p over q to the q, I just take the 1 over qth power of both sides. And that's what I wanted to show.
Nice.
Okay, so once, I haven't told you what e of 1 is, but once you know that, you know what this function does at every rational number. Um, okay, what other properties do we have? 6? Oh, 6 is 6 is a little bit harder. Um, are you interested in that, or do you want to move on to trig functions? It's not that hard.
Uh,
I don't know that it's that interesting
I think
though.
I'm.
You
I
satisfied
think I'm
with?
more interested in seven
Oh
than
well,
6.
the whole point is that I did 6 in order to do
Uh,
7. So the first limit
okay. Okay.
follows immediately from 6 because
Oh.
a 1 plus x definitely goes to infinity. And then the second limit
Yeah.
is just, yeah, 1 over a thing going to infinity. So I guess we're also using number 1 there, but 1 over a thing going to infinity goes to 0.
Sense.
All right. So yeah, maybe we move on to trig functions because those are a little more intricate.
Okay.
But any questions from Matias or the chat about these exponential functions? I selected
I suppose this
the
isn't
box again.
really
Yeah.
dir directly related, but why did you pick to negate how these properties follows from this particular definition versus the other ones? I know you just like the function kind of definition, or why didn't you go with the
Y-
limit definition, for example, or
Yeah, so why did I use this definition? Because it was because I learned about this easy way to prove number two using
mm-hmm.
this definition. Um,
uh,
I think,
so you're like, I want to know what if I can prove everything that I know about it from it.
yeah, I think proving the other things would be using the other definitions would be harder. Like
Mm-hmm.
if you look at the power series for e to the x, how do you show
Yeah.
that that thing is positive everywhere? That's not at all obvious to me. I think this is the easiest way to prove all of these properties. So I guess
I
maybe
like it.
it you could prove all of these mm, sort of just by defining e and then defining e to the x as well. Yeah, how do you define? Okay, so you could define. Hmm, I don't know. I think it's tricky to prove all these properties starting with a different definition. Now, of course, there's something, elephant in the room. We're assuming that there is a function that satisfies these properties. That has to be
Yes.
proven.
Okay. Mm-hmm. Mm-hmm.
And I would say probably the easiest, or the way that appeals to me the most, is to build up a theory of power series and then show that the sum of x to the n over n factorial satisfies this differential equation. So that has to be done.
Yeah.
But okay.
I thank you for this so far. I don't think I've ever seen all of those properties derived explicitly, so that's cool. You said you can also do it for big functions.
Yeah. What is going on with this?
Are you gonna split up the exponential function into sine and cosine?
I'm not doing anything complex, if that's what you're asking about.
Okay.
Although that's a nice way to prove a lot of stuff about trig functions. But I'm keeping it real. What is going on with this text in the middle of the? Can you like? I can't erase it.
Either. You know how to erase permanent marker off of a whiteboard? Let's try it. You're right there with that.
Yeah, right on top
Right
of
at
it.
the normal marker, and then you erase that. Oh, didn't work.
No. But you like it looks like you had selected it somehow. Is this a text object?
I was trying to lasso it, but it wouldn't work.
Why does it keep Wait. Like it keeps Whenever I touch the screen, it switches back to... Oh, yes! I don't know how I did that.
You also removed the whole box.
Damn it.
Maybe it was like a title of the whole box.
Oh, it is part of the box, isn't it? Um,
Yeah.
what the heck?
And what even is that first character on there? Negative tau?
I think it's a T, but there's a little pen mark there too. Now you should see. It's just
Uh,
a minus T.
yes.
Okay, so that's just on the screen now. Nothing we can do about that. Um, you would think that Miro would be better by now. It's been around for so long. Okay, so let's do the trig functions. It's a little more fun. Similar
Mhm.
ideas, but okay. So I'm gonna let uh, s of x and c of x, obviously meant to suggest sine and cosine, be differentiable functions such that s prime of x equals c of x for all x, c prime of x equals this is driving me insane. Uh, minus s of x. I don't mind if it like stops working every once in a while, but sometimes it's like every
Right,
other
right.
pen stroke. And like somehow now I'm
So you're
selecting the whole box. Okay.
you're
And
not going to use the exponential stuff, right?
right.
Okay, so you're doing it. Oh, nice.
Yeah, it's logically independent, but it's using similar
Hmm.
ideas. So and of course I need my initial conditions. S of 0 is 0 and C of 0 is 1. Okay. You ready to have your mind blown?
Yeah.
Here, I'm going to tell you what number 2 is. Um, so number 2 is going to be that these functions s of x
Hmm.
and c of x are both trapped between negative 1 and 1. So, worth pointing out,
Oh,
I like if you look at the power series for sine and cosine, I don't know how to look at those power series and deduce this.
that's a good point.
Like
That's
it's an alternating sum of powers with factorial coefficients. Like why should that be between negative 1 and 1?
right.
And you know that it does hit both of these values, so like it's delicate. It's not some
Mm.
crude approximation.
They're tight approximations.
Yeah, they're sharp. Okay, so number 2 is going to
I've
be a.
heard the word tight as I think the word tight is what analysts use or bounds when they're hit.
I think sometimes they also say sharp, but
Okay,
yeah,
nice.
we know what we mean.
Yes.
Okay, so number 2 is going to follow immediately from number 1, which is that s of x squared oh my goodness. And the keyboard on my iPad keeps opening, and it now I have a different pen selected. I'm writing in disappearing ink for it's doing some sort of handwriting thing, and that handwriting is getting converted to text, which now that text also lives in the middle. At least this I can backspace. The other text might be hopeless. Wait. Yes.
Whoa, good job.
Okay. This is real spooky though. Okay, s of x squared. I should really just like have you start writing for me. But here, do you want to try this, Matias? You want to try
I'll be your
writing?
scribe.
You can be the scribe. Okay. So you agree that number one immediately implies number two?
Yes.
Yeah. Yeah. If you have a number bigger than one or less than negative one, you square it, you add something to it. You're not getting one. Okay. Um, so number one, of course, is interesting, not just because it gives us the bounds on sine and cosine, but right, that's the Pythagorean identity. This is the most important trig identity, if you ask me. Okay. So,
Yeah.
Matthias, I'm just going to have you differentiate the left-hand side of that equation. Digital voodoo. Yeah, Mean Machine Rex is right. There's some spooky business going on here.
Getting late, so bear with me. 2 times sine of x,
Yeah, so you're applying the chain rule.
and then right, and then yeah, subtract one
This is
from
a
the
good
power.
refresher if you're teaching calculus in the
I'm
fall.
supposed to be, yeah. Derivative of sine is cosine. I still remember that.
Well, no,
Oh,
you don't need. You're not remembering that. That's written at the top of the page. That's like one of the only four things we're assuming that the derivative of s
that's right.
is c.
I don't even have to. I
Yeah,
don't
yeah.
even have to remember how to
We
do
don't
it.
know. Yeah, we haven't. I haven't told you what s and c are. I'm not
hmm
saying anything
hmm
about opposite and hypotenuse and
hmm
adjacent. I'm just
Well,
saying.
I suppose
Suppose that
I'm
they.
supposed to remember. I'm supposed to remember the chain rule, though.
You are supposed to remember the chain rule. Yes.
hmm
Okay, so you don't want to set that equal to 1 because differentiating just you're just differentiating
That's
the
right.
left-hand side.
Is 0.
And yeah, that's definitely 0. Right? That's
Yes.
it's just
I
2 s of x c of
It is
x minus
0.
itself.
Right.
That's
hmm
0. So that tells us
Yep.
that s of x squared plus c of x squared is a constant. Doesn't matter what value of x you plug in, you always get the same result. Now, how do I know that that constant is 1?
Well, it probably should use the other facts that we know.
Yeah, if you just plug in 0, you
So,
get 0
hmm
squared plus 1 squared, which is 1.
Well, yeah, I won't go back and hold that out again. I'll say
Yeah, when you plug in x equals 0, it tells you that the
mhm.
value of the constant is 1. So obviously, right, this
Cool.
is not to like discount, you know, the geometric interpretation of sine and cosine, or to suggest that this is how we should teach sine and cosine. That would be a terrible idea. But I just think this is
I think we
so,
should just teach all functions without ever knowing what they look like.
yeah,
Just
for sure.
assume they exist and done.
Yeah.
I mean, show that they exist, and then we're good to go from there.
Right. And again, you
We don't need to
prove that
visualize.
such functions exist by defining the power series and checking their
Yes, yes.
derivatives. But yeah, this is nice because like obviously this Pythagorean identity is like, the geometric interpretation is this is the Pythagorean theorem applied to a triangle with
Mhm.
a right triangle with an angle of x in radians. But it's just such a cool idea that I didn't know about until like earlier this year, is that the Pythagorean identity is forced, like immediately forced, just by the fact that the derivatives are what they are and the initial conditions are what they are. That's all it takes.
Hmm.
Tell me this isn't one of the coolest
Hmm.
things you've ever seen.
It's not. See, that's what he told me to tell me, or tell you what.
Oh, wait. Yeah, it's a dare. I dare you to tell me
Oh, okay.
this is not the coolest thing you've ever seen. And it's a dare because that's a dangerous thing to do. It would be crazy to claim that this isn't one of the coolest things you've ever seen.
It's
Should
just
have known
doing
you would
history
take me
backwards.
literally there. What? Oh.
I mean, we're doing all this calculus to be like, take that, Pythagoras.
Yeah. Well, I mean, you know that this is like how I operate as a mathematician, like as a student of Kate Ponto, is that I look at math that other people have already done and then try to figure out like the most bare bones way to present it. Sort of deduce everything from formal formal nonsense. I think you can understand why this appeals to me.
Yeah,
Maybe if you don't
yes,
love it
I
quite as
do.
much as I do, but
I think it's cool,
it
but
is. Yeah,
yeah.
it's not like useful as like I wouldn't show these ideas in a calculus course. I might include them toward the end of my real analysis course in the fall. Um, but we'll see. All right, so you'll recall that one of the first things that we did with exponential functions was to prove something about
Oh
e of
yeah.
x plus
Hmm.
y. The analog, of course, is
Yep.
the angle addition formulas, which are that s of x plus y is s of x c of y plus 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 c of x s of y. And of course, if you make it a minus, that becomes a minus. You know the other one off the top of your head, right? Do you want to write that for me?
I don't remember it off the top of
Ooh,
my head.
that's that's embarrassing. So c of x plus y, x plus or minus y is. And again, if any other people are watching this, I want to reiterate, like Matias is a friend of mine from from grad school. We've known each other for 9 years. I make fun of him sometimes. I don't. If anyone in chat doesn't remember this formula, I want you to know that I'm not judging you. I'm only judging Matias.
Yeah.
Yeah, so it's got the minus plus instead of the plus minus. Yeah,
Hmm.
Mean Machine Rex. There's a real analysis lean game. I have not played through
I'm
that one
just
yet, but I'm excited to.
just now finally understood why I have math anxiety. It didn't start till I sat next to you.
Oh dear. um, wait. Yeah. No. Yeah. That's it's probably my fault.
Had nothing to do with failing prelims enough times.
So for the first one, and I mean specifically with the plus, what you do is you run the same sort of argument that we've run several times now, showing that a function is constant by proving that its derivative is zero. This one I did not come up with on my own. I found this on Stack Exchange. The function that you look at is s of a plus b minus x times c of, sorry, trying to find it in my notes, times c of x. That looks a little complicated, right? That's only half of it. Plus c of a plus b minus x times s of x. Okay, so this is a little more involved. We're not going to walk through all the details here, but the point is, if you computed the derivatives using only these assumptions,
Okay.
and the chain rule, like you're allowed to use the basic facts of calculus, you would just get zero, telling you that this thing is constant. And then you plug in zero, and you'll get using the initial conditions, you'll get the left-hand side of the angle addition formula. If you plug in x equals
Okay.
b, you get the right-hand side. So that's how you prove this angle addition formula.
Okay.
And the other three angle addition
You just have to be
formulas.
clever and
What?
yes, it's one of those proofs where like you just have to pick the clever function and then
Yeah.
apply
And
it.
yeah, I as I mentioned, I did not come up with this one on my own, but once you
Mhm.
have this one, you would come up with the other three. The one
Okay.
for a minus sign here, and then both of them for cosine. They're they're very
Yeah.
similar. In all cases, you're looking for a function. Yeah, you'll see the pattern. Um, and yeah, you're always going to plug in 0 and b once you know that the function is constant. Okay, so that's neat. Like, again, imagine trying to prove that from the power series for these two functions. I don't even. I have no idea how you would do that. Okay. What do you want to prove next, Matias?
Um. hmm. Well, I don't know, something about like periodicity would be cool. Like that they're periodic in some
Yeah,
sense.
we're gonna build up to that. Um,
Okay.
but yeah, that's
What do
definitely
we
what I
have
wanna. I
for
wanna get
that?
to that.
Mhm.
Um, oh no,
What would we need for
there's.
that?
I accidentally made more text in the middle. There's just a J in the middle now. I'm sorry, I don't know how I'm doing this. Okay.
Get with your initial.
Yeah, I mean, it of all the letters we could have ended up with in the middle, it is the best one. Oh my goodness.
So what would we need in order to get the fact that they're periodic, or what other properties would be helpful towards that?
Yeah.
Trying to think.
Okay.
I mean, probably we're gonna use the angle addition formulas or something.
Uh-huh.
But what else do we need?
Okay. So yeah, let's talk about that. So how would you use the angle addition formula to show periodicity? Like, what do you want the final computation to be? to show that it's periodic. Like, what does it mean for it to be periodic?
Mm. Well, I want that with multiples of uh, pi, I guess. Going to be the return to the same value.
Yeah. So like, what it means for it to be periodic with period 2 pi is that for any x, s of x plus
Pi,
2
yeah,
pi is the same as s of x, and the same for c of x.
right.
Okay.
Hmm.
So we have an angle addition formula. What do we need in order to check that?
Well, we need x plus 2 pi, and we need to see that it comes to the same value.
Yeah, yeah. So, yeah, I mean, if you write this out, right, like you're gonna get s of x times c of 2 pi plus. So you want c of 2 pi to be 1, and you're gonna get also a term c of x times s of 2 pi. You don't want that cosine in there, so you want s of 2 pi to be 0. So
Yes,
we need to know the values of s and c at 2 pi. And then there's of course a more fundamental
that's true.
question that suggests. Maybe.
Well, we need to know the values of sine at 2 pi.
Yeah, we need to know the values of s and c at 2 pi, but I guess what I'm getting at is we need to say what pi is. um,
Okay, yes. Hmm.
which from one point of view that is kind of silly, but I guess like how do you this is an interesting question. How do you define pi when you're doing analysis? I'm
Is
not like asking how is pi
it
defined. I'm asking how do
different?
you think of like what pi means?
I mean, I don't think of it as different than the geometric definition.
Yeah, I
And
guess.
honestly, I forget the definition and then just move on. Or like I don't consider the fact that it's the ratio between the circumference and the diameter.
Yeah, I guess just what I'm getting at is like if you want to use that definition to prove analytic things, it that just feels to me very hard to work with. Like the circumference of a
Mhm.
circle. I mean, I would to describe that analytically, and like in a way that I could translate that idea and
Mhm.
work with it here. I would want to like write that as an integral. I assume of like root
Mhm.
1 minus x squared.
Mhm. Well, I like Mean Machine Rex's idea of rotation. Like you can think of
Yeah. So like, what do you?
active rotation.
How do you translate that into to something that you can work with here? Like, how do you use that and show that s of 2 pi is 0 and c of 2 pi is 1, just using what we have? See, like, yes, obviously that's what pi is. Like, that's, the same way that, you think of trig functions in terms of triangles. when you first learn about them. You don't start about by learning them about the way that I'm talking about them now. Yeah, you think of pi as the ratio of the circumference to the diameter, but I've never really like understood how to like shoehorn that notion of pi into analysis proofs, you know? And I don't know that I don't know if it just that's not a good definition to use in analysis or if I just don't know how to use it that way. But what I'm going to do is I'm actually going to define pi. I'm actually going to define pi over 2 as the first positive zero of the function c of x. That's
Okay.
how I'm going to define it.
Okay.
And then, well, that will lead to all of the familiar, values of the trig functions at all the nice angles you know about. And then from there, you could compute the circumference of a circle with an arc length integral, which you probably use a trig sub to do, and you're going to end up getting, pi as the ratio there. But so I guess what I'm saying is I only know how to work this one direction, starting by defining pi as the ratio, or sorry, as the first zero, the first positive zero of the cosine function, and then getting everything else, all the other characterizations of pi from there. I don't know that this is the only way to do this, or the best way to think about pi. Even in
Yeah, I
this,
was thinking like a power series approach because there are a bunch of uh, power series that evaluate to like pi over 4 or something,
oh, for sure. But
or
even
certain
there, I
values of
still
x. Maybe.
like, how are you going to evaluate these functions s and c at some power series?
Yeah, yeah.
Um, if you figure out how to
I
do
like
that,
your
let me
your
know.
approach.
Yeah, so I'll show you my approach, and yeah, if anyone can tell me how to do the sort of the reverse approach where you define pi more geometrically and then go back to the analysis. If anyone can tell me how to do that, I would love to know. But first, I'm going to prove that sine is odd and that cosine is even. That'll sort of simplify some of the analysis of that's leading us toward periodicity, but it's also just a good thing to know. And this is maybe my favorite proof that we're going to do tonight because it's really there's a clever way to reduce it to something we've already done. So I'm going to define two new functions. One of them is s of x plus s of minus x. And my goal is to show that both of these functions that I'm defining are 0. So showing that s is odd is the same thing as showing that f of x is identically 0. Matias, can you hear the concert going on outside my office at all?
No,
Okay, it's not getting picked up.
no.
Yeah, the football stadium is like diagonally across from my office. There's a concert going on there right now. Um, as long as it's not distracting other people, I'm happy. Okay, and then I'm going to define g of x to be c of x minus c of minus x. And again, showing that c of x is even
Hmm.
is equivalent to showing that g of x is 0. Now you might think, how do I show something is identically 0? Well, our strategy has been to show that the derivative is 0 and then use an initial condition. But what do you get, Matias, if you differentiate f?
Cosine of x, or sorry, d of x plus negative c of x.
Almost. You get minus c of minus
Plus,
x. You get g.
Oh, yes, yes. Sorry. Yeah, it's being late. That's there's a negative inside this. Yes, of course. So
So if you
yes.
differentiate f, you don't get 0, obviously. You get this other thing that we're hoping is 0. And if you differentiate this
Mm-hmm.
thing, you don't get 0. You get the first thing, which we're hoping is
That's F.
0.
Yeah. Mm-hmm.
So there's no,
Mm-hmm.
right, that doesn't do it. But what I'm gonna observe here, this is so clever, and I did not come up with this myself, um, but we saw that f prime is g, and g prime. Sorry, I think I said you get f of x. That's not quite right. You get minus f of x. And maybe let me also just point out for fun, f of 0 is 0. G of 0 is also 0. I have my initial conditions, so I can just evaluate these things at 0. What do you notice? Do these equations remind you of anything?
They do. They remind me of S of X and C of X.
Yeah, they're related to each other exactly the same way that S and C are related. The only
Yeah.
difference
Hmm.
is our initial conditions are slightly different.
Right.
But and you could write this out in detail if you wanted, but you don't have to, because if you ran exactly the same argument as in number 1, where we showed the Pythagorean identity, if you run exactly
Hmm.
the same argument, you learn that f of x squared plus g of x squared is constant. And what's the value of the constant? It's not 1 like it was last time. It's 0.
It's 0. Yeah.
And if you have a sum of two squares being 0, the only way that happens is if they're both 0. So we
Yeah.
knock out both of these tasks at once.
Oh. Ha.
So we did
That, that's good.
we did
Hmm.
both of them at once, and we didn't even do anything new. We just we noticed that it's the same argument as before.
Hmm.
That's my favorite one. Um,
That's a good one. Yeah.
okay. So number 5, we're gonna analyze the zeros of s of x and c of x. Okay. So I said before when we were talking about pi that I wanted to find pi over 2 as the smallest positive zero of c of x. What do I need
Hmm.
to prove for that to be a valid definition?
Hold on. I was trying to. You're saying of C of X or S of X.
C of x. Pi, right? Pi is the smallest
No.
positive zero of
Pi.
s of x,
Right.
but I'm going to define pi over 2 as the smallest positive zero of c of x. It's just going to be easier if I go with the first place where either of the functions is 0.
Okay.
That's not a valid definition until I prove something.
Hmm.
What do I need to prove?
Okay. Sorry. Can you repeat the question? I was having to go to the unit circle again in my mind.
So we're going to define. My question is, what do I need to prove in order to make this definition, which is that pi over 2 is the smallest positive zero of C of x?
Well, we first need to prove that it is a zero,
Yeah, that's it.
and then that it's the smallest one.
And then there's a little bit of analysis. Like this is the first time maybe where, and I think the only
Mhm.
time where like we actually have to talk about like the completeness of the real numbers. Um,
Hmm.
um, the set of all positive zeros of C of x is of course bounded below by zero, so it has an infimum, um, and the infimum is also a zero by continuity. So that's a little detail here that you know if you haven't, if you're watching this as someone who's just had Calc 1 but not taken real analysis, this is like a little detail you don't maybe need to worry about. It's relies on the screen moved again. Relies on some properties of the real numbers, but I hope you'll accept this as plausible that there is a well-defined smallest positive zero. As long as I know that there is one. If there weren't any zeros, this wouldn't make any sense. Okay, so claim C of x equals 0 for some positive x. Okay, and I'm going to argue this by contradiction. Oh, we're out of space. So let me erase the left-hand side. So let's say, suppose that there's not any zero of the cosine function, at least for a positive x. So I'm gonna deduce a few things in sequence, but first maybe let me sketch. Oh, can I not do a straight line easily? Okay. Let's sketch.
It's under shapes if you want it above the
Oh,
pen.
that seems too complicated.
Okay.
I'm already struggling enough as it is with Miro. Whoops. Okay, so I know that S of 0 is 0, C of 0 is 1. I know that both functions are trapped between negative 1 and 1. So, okay, what can I conclude? C of x is positive for all positive x. Because if it was ever negative by the intermediate value theorem, it would have to be 0.
Yep.
And I'm assuming that
Mm-hmm.
that's not the case. Okay, so C of x is always positive. That tells me, oops. I also know that S of x is always positive. How do I know that? Well, S of x is never 0, because by Rawls' theorem, that would make C of x 0 at some point.
Mm-hmm. Yeah.
Rawls' theorem, of course, being the special case of the mean value theorem. So S
Right.
of x is never 0.
But the endpoints have to be the same, right?
Yeah, exactly.
The
That's what
same
Rawls' theorem is, yeah. So S of
height.
x
Yeah.
is never 0 for positive x. It's also never negative, because then by Rawls' theorem, or sorry, the general mean value theorem again, that would force C of x to be negative at some point. And by the intermediate value theorem, that would force c of x to have a 0. So I can conclude that s of x is always positive. But I also know that c of x is positive, and c is the derivative of s, so s of x is always increasing. So s is positive and increasing. And of course, it's bounded above by 1. So it's going to look something like that.
Mm-hmm.
There's no logical contradiction yet, but there will be once I start thinking about c of x.
Okay.
So c of x is always decreasing. I know it's decreasing because its derivative is minus s of x. S of x is positive, so the derivative of c of x is always negative.
Mm-hmm.
It's also always concave down because c of x it is positive, and its second derivative is minus c of x. So the second derivative is always negative. So c of x has to be always decreasing and concave down. A decreasing concave down function is always gonna
Yes.
hit the x-axis at some point.
Yes, of course.
Right? Like, and if I want to do this carefully, I just like pick any positive x value, whatever that s of x is, it's c of x, or it's positive, and that's an upper bound for the slope from there on. So, and I can extend that straight line, and it's good. C of x is going to have to hit 0 before that.
Yeah.
So there we go. So c of x, we got a contradiction, assuming, which is a funny kind of contradiction proof. Assume that there's no 0, and then you prove that there is. So if it has a 0, you're done. If it doesn't have a 0, it actually does have a 0 anyway. I just think that's a very funny kind of contradiction proof. Anyway, so it has a 0. So my
just kidding. There is one.
Yeah. So my definition. My definition is valid. Woo. Okay. Oh my goodness. All right. My definition is valid. Pi over 2 I can define to be the smallest positive 0 of c of x. Matias. So I know that c of pi over 2 is 0.
Mm-hmm.
What does that tell me that s of pi over 2 is?
Well, I of course know the answer, but why?
There's a very easy reason, using what we've already proven. Using actually even the first thing that we proved. This is not fair. I've erased it. It's not here anymore.
I can't remember that far back.
We started by proving the Pythagorean identity.
Yes.
What does the Pythagorean identity tell me here?
Well, c squared plus s squared is 1.
Yep.
And so c pi over 2 is 0, and so the other one has to be 1.
1 or negative 1. So the Pythagorean identity alone just tells me that s of pi over 2 is 1 or negative 1. Why is it not?
Right.
Why is it not negative 1? Well, because if sine were negative 1 here, then because sine goes positive first, there would be a 0 somewhere before pi over 2. And then by Rawls' theorem, there's a horizontal tangent line somewhere even before that, and that would force c of x to have a 0 before its first 0. It'd have to have a
Yeah.
0 at a smaller x value than the
Yeah.
smallest x value
Yeah.
where it has a 0.
Mhm.
So that's a contradiction. So that's why it can't be -1. So we now know it's 1. I've added a another I to the text in the middle. Oh, there's another one.
And you move
And I moved
the whiteboard again.
All right, close enough. Um, oh, geez. Yeah, my app is glitching. It's like the toolbar is all zoomed in, so I only see the top half of the toolbar. That doesn't make any sense. All right. I've restarted the app. Thank you. Plus or minus 1. Thanks for filling that in. Of course, we walked through the argument that it actually is positive
Yes.
1. Okay. And now the angle addition formulas. Give the values of S and C, at all integer multiples of pi over 2. Oh, that was going so well. I thought maybe after restarting it would work, but no. Okay, so we don't need to write out those formulas. It's pretty straightforward. But we now know the values of C and S at all, at pi over 2, pi, 3 pi over 2, 2 pi, etc. And that actually is enough to give us periodicity. Because that's going to tell us that C of x is, C of 2 pi is 1, and S of 2 pi is 0, which tells us, again, using the angle addition formula, that S of x plus 2 pi is equal to S of x, and C of x plus 2 pi is equal to C of x. You might also ask, like, how do we know... Oh, Rex, yeah. That's a good suggestion, to use a Wacom tablet. And instead of writing on my iPad, just, write on, do it on my browser with a Wacom tablet. I do actually have a Wacom tablet, so it's right here.
I was using it. I guess it worked for me.
It worked for you, yeah. I'm curious if that would... Oh, yeah, because it keeps getting moved because I'm doing... Yeah, I'm moving it by doing something weird on the iPad. That would probably solve all of my issues. Maybe I'll give that a try next time. That's a really good suggestion. Thank you, Rex. But I mean, we can basically wrap up here. So we've shown that it's 2 pi periodic. We should argue for completeness that it doesn't have any smaller period. And like if we really want to understand the shape of these graphs, you know, we where they're increasing and decreasing in concavity, we need to be able to say where S of x and C of x are positive and negative. And that's pretty easy once we know that we've found all of the zeros. Like if there were a bunch of other zeros between 0 and pi over 2, the function could have a really high period. A period much smaller than 2 pi. Am I making sense? But I mean that's
Sleepy brain, yeah, kind
fairly,
of.
yeah. It's pretty boring but straightforward to rule out. Like I know that cosine doesn't have any. I know that C of x doesn't have any smaller zeros by definition. Pi over 2 I've defined as the smallest zero. I also know that S of x doesn't have any zeros, like between 0 and pi over 2. So I guess on my graph, pi over 2 is like right here. I know that S of x is not 0 here. For the argument I've already given by Rawls' theorem, that would force a smaller 0 for C of x. I also know that there aren't any zeros between pi over 2 and pi. Basically because if you had a 0 here, that would put another 0 at pi over 2, or sorry, at pi minus that x value. And that's just a consequence of the angle addition formula. And similarly, I can rule out zeros between pi and 2 pi for S of x, because like a 0 at pi, at 5 pi over 4 would force a 0 at pi over 4, which I know doesn't happen. So you can pretty quickly rule out the existence of any other zeros besides the ones that you know about and multiples of pi over 2. And that shows you that 2 pi actually is the smallest period of this function. That's like a really nitpicky thing.
I'm just imagining an alternate history kind of where we didn't know what the zeros actually were beforehand, and we're just like, well, this would be a cool function to define, and then we start playing around and trying to figure it out. I guess that's kind of what you're doing, but you do have the advantage of knowing in advance what you're aiming for. But I was just
Yeah, so I wonder if there is any like sort of, history like that. I mean, so what I'm thinking is, in physics or other places where differential equations show up, you start with a differential equation and you try to solve it.
yeah,
And like
yeah,
sine and cosine functions are solutions to you know the those are the motion of a simple harmonic oscillator. So I'm curious, what the history is for the understanding a simple harmonic oscillator. Like, did anyone actually like have the differential equation and wonder what the solutions were? Surely we knew about sine and cosine functions long before that. Yeah, I don't know that this alternate history. I think it is an alternate history. Is what I'm saying. I don't think this ever actually happened. But yeah, so if we wanted to keep going, which I don't, and I'm sure you don't, because it's what, almost midnight over on
yeah.
the East Coast. Um,
It was a long day if you can't tell, but it was fun.
yeah. Oh, sorry,
Uh,
sorry, sorry. What I was gonna say is, if either of us had the energy to keep going, what we could do is deduce the values of sine and cosine at the remaining special angles, like all the multiples of pi over 4 and pi over 6. We
Mm.
should be able. I didn't actually work all of that out myself. I figured you and I could figure it out together using the angle approximation or the angle addition formulas. But that would be the that's the homework for anyone who's still with us um, and is interested. See if you can use what we've proven so far to come up with the sine of pi over 6, sine of pi over 4, etc. Yeah. Any final thoughts, Matias?
I learned a thing or two. I had fun, and I'm gonna have sweet dreams now.
Oh, I bet you will. Yeah, it's dangerous thinking about math this much, this close to bedtime. Um,
Yeah.
do you do you have the math dream sometimes where it feels like you're doing math, but you wake
Yeah, and
up
you
and
think
it's
you discovered something amazing, and then you wake up and think about it, and you're like, that was idiotic.
all
So,
right. Good night, Rex. Thanks for watching. Um, yeah, and like for me, it's like it's always an unpleasant dream. Like it feels just like feverish. Like it's not restful. I
well,
haven't.
yeah, I have two different types. One is like I discover something amazing and think I'm a genius, and then the other one's like I can't even. I'm like struggling to, like, it's that dream where you're struggling to run, but you can't run, but
Oh
like you're
yeah.
doing math, but you can't do math kind of dream. It's terrible.
I'm happy to say I have not had one of these math dreams in a long time. Um, I don't do that much. I haven't done a lot of research recently. That's probably why. Um, but yeah, so why don't we call it a night? I'll end the stream in a moment. Matias, if you want to stick around for just a minute to debrief, and then I'll
Sounds good.
let you get to bed. But thanks everyone for watching. I am doing another stream tomorrow evening. Instead of Matias, I'll have as my guest another grad student friend of mine, Shazad. He and I are going to talk about um, college algebra, which is one of the courses I'm teaching in the fall. And we're going to talk about, like, what things. He's helping me plan for the fall semester. Like, what things do I want to cover? How am I going to structure the class? But more interesting questions like, why do we cover these topics? Like, what are interesting ways to motivate these topics? Are there like good real world examples I can use to introduce these topics that feel authentic and not contrived? So that's tomorrow at the same time, which I think is 7 p.m. Mountain. Yeah, thanks for watching.